Hi, this video is about acid-base property of salt solutions. So we are in chapter 16 in the Brown and LeMay book, and this is section 9. All right, so let's talk about salt hydrolysis. Well, first of all, what is a salt? Well, it's an ionic compound. They are strong electrolytes. They completely dissociate into ions when you put them in water. So a salt, if you remember from General Chem, is a metal and a nonmetal. And then we call salt hydrolysis is the reaction of the anion of the salt or the cation with water, and it will produce either hydronium or hydroxide ions in the water. And so because of producing those hydronium or hydroxide ions, they can affect the pH. So let's look at anions first of all. So let's say that we had a 0.01 molar solution of sodium fluoride. That's a salt, an ionic compound, and it completely dissociates in water. Sodium fluoride is soluble. So the sodium ion right now, we're just going to ignore. We're just looking at the anion. So fluoride ion is the anion, and fluoride is the conjugate base of hydrofluoric acid, and that's a weak acid. So let's first of all write the hydrolysis equation. So we have the fluoride ion in water, so we're going to write it as HOH, and that is an equilibrium reaction, and it's going to form hydrofluoric acid because the fluoride ion is acting like a base, and it's going to take a proton from the water and leaving behind hydroxide in the water. So what that does for us is it makes, we start off with the fluoride ion, which is our base. Water is going to act like the acid. And then once this proton is transferred to the fluoride ion, this forms the conjugate acid, and there it is. There's what's going to affect our pH, that hydroxide ion, and that's the conjugate base. So let's look at what's happening here. This fluoride ion, this is a conjugate base of a weak acid. And so conjugate bases of weak acids in water will make the acid and hydroxide ion. All right, so here are some other examples of salts that can produce a basic solution. And so again, we're looking at the anions. So we've got the sodium acetate here with the acetate, which is going to form hydroxide ion. The carbonate, when you put it in water, it will form hydroxide ion, and the cyanide ion. All of these things that I have circled, these are anions that are conjugate bases of weak acids. Okay, so I want you to do a little bit of homework here. I would like you to write the hydrolysis equations for those acetate, carbonate, and cyanide ions. And then for each of those, identify in your reaction the acid, the base, the conjugate acid, and the conjugate base. So do exactly what I did with the fluoride ion. So you're going to have 3 equations when you're done. Okay, well now let's go ahead and calculate a pH of these of this solution. So let's go ahead and start with a problem. We have a 0.15 molar solution of sodium fluoride. So what in that sodium fluoride is going to affect your pH? Well, we're going to talk about our fluoride ion. So let's first of all rewrite our equation. There we go. Now, what we're going to do is we're going to start with our 0.15 molar solution of fluoride. Water is not going to affect our icebox. We don't have any of this when we start. And then we have X and X, and this is minus X. And then at our equilibrium state, we have X and X and 0.1 minus X. Well, how are we going to figure out what X is? If we know what X is, we'll have our hydroxide ion concentration. Well, we're going to set it equal to the K, and in this case, it's a KB. It's a Kb for the fluoride ion. Well, we don't have the Kb for fluoride ion, but we do have the Ka for its conjugate acid. So if you remember, so first of all, this Kb is going to equal x squared divided by 0.15, and we're going to drop that minus x because it's going to be so small. And we'll make sure that it is when we're done, that we can ignore it. All right, but we don't have a Kb for fluoride, but we do have the Ka for hydrofluoric acid. And if you remember this relationship, the Ka times the Kb equals Kw. So if I wanted the Kb, I would set it equal to Kw, which is 1 times 10 to the negative 14th. And we're going to divide that by the Ka of hydrofluoric acid. So go into your acid-base table, and when I looked that up, it is 6.8 times 10 to the negative 4th. All right, so the Kb for this is 1.47 times 10 to the negative 11th. All right, so we're going to plug that into our equation, and so our x, which is our hydroxide ion concentration, our x is equal to the square root of the Kb, 1.47 times 10 to the negative 11th, times our initial concentration of our fluoride ion, which is 0.15. And when we solve for x, we get 1.48 times 10 to the negative 6th. All right, that is our x, which is what we're interested in, our hydroxide ion concentration. So from here, we can take the negative log of that, and we're going to get a POH, and our POH should be between 5 and 6, and it winds up being 5.83. And the question asked us for the pH, so the pH is going to be 14 minus our POH. I didn't mean to do that. And I've lost all that. So hopefully you've been writing this down as you've gone along. So our pH is going to be 14 minus our POH. So the final answer to this question is 8.17. So the pH of a 0.15 molar solution of sodium fluoride is 8.17. It's above 7. It's slightly basic. And that's what we're going to expect. For the conjugate base of a weak acid, we're going to expect a basic solution. All right, let's look at salts that produce acidic solutions. And the salt that we're going to look at is something that has the ammonium ion. So ammonium ion will produce hydronium ions in solution. So here we've got the equation down here. We've got the ammonium ion, and in water, what's going to happen is that ammonium ion is a proton donor, and so it will give away, because it's acting as an acid, it will give away its hydrogen and its proton to the water, and it's going to leave you with ammonia, and that's a nice weak base. And here's what we're interested in. These hydronium ions, these are the conjugate acid, and if we can get their concentration, we can take the negative log of it and get the pH. So let's go ahead and do that. So we're going to start again with our equation, our equilibrium equation of ammonium in water from our last slide. I'm going to write water like this. It's going to form ammonia and hydronium ion. Okay, 0.05 molar X and X, and nothing. And it's going to be at equilibrium. This time it's a Ka. A Ka at equilibrium is going to equal x squared divided by 0.05 minus x, and we're going to drop that minus x. We need the Ka for the ammonium ion. I couldn't find a Ka for an ammonium ion on my acid chart, but I did find a Kb for the conjugate base, ammonia. And so we can get the Ka by taking the Kw and dividing by the Kb of ammonia, and that Kb is 1.8 times 10 to the negative fifth. So when I plug in my Kw and I plug in my Kb, I come up with a Ka for the ammonium ion of 5.56 times 10 to the negative 10th. All right, so let's go ahead and do that math. So our hydronium ion concentration, which is equal to X, is equal to the square root of our Ka, 5.56, times 10 to the negative 10th. That's a tenth, times our initial concentration, 0.05. And when I do this, I come up with a hydronium ion concentration of 5.27 times 10 to the negative 6. That is a hydronium ion concentration, so the negative log of that will give us our pH, and our pH of that ammonium solution is 5.2, I think it's a 5.28. Okay, so there we go. That's an acidic pH. It's below 7, and the ammonium ion was acting like an acid, donating its proton to water, so I would expect a pH below 7. All right, so just very quickly, usually metal ions do hydrolyze in water, and they will form acidic solutions, but alkaline metals and alkaline earth metals, their hydrolysis is so small that they're not going to affect the pH. Okay, but metal ions that are commonly used and form acidic solutions are something like aluminum with a +3, or chromium, or iron 3, and bismuth 3, or beryllium 2. So these are cations that if you put it with an anion that was neutral, you would have an acidic solution. Okay, let's talk about solutions that form neutral solutions. So if you've got that cation of an alkaline metal or an alkaline earth metal, they don't hydrolyze to form any protons. So that would not affect the pH. So sodium, potassium, magnesium, calcium, anything, those ions will not affect the pH. The conjugate bases of strong acids are so weak, I like to say they're pathetic bases, that they do not make any measurable amount of hydroxide ions in solution. So conjugate bases of strong acids are not bases, okay, in solution. Okay, now we'll talk about this at another time. Let's go back to this. So solutions that form neutral solutions would be something like, say, sodium chloride. Salt, good old table salt. The sodium will not form any hydronium ions in solution. The chloride ion is the conjugate base of a strong acid. Conjugate bases of strong acids are so weak they don't make hardly any hydronium or any hydroxide ions in solution. So it's not going to act as a base. So the pH of a salt solution, sodium chloride, would be 7 because nothing here is going to hydrolyze. Let's do calcium nitrate. Again, That nitrate ion is the conjugate base of a strong acid. It will not form hydroxide ions because it is such a weak base. And the calcium ion won't do anything there. Okay, so I hope you've got a good idea of how these weak acids, how their conjugate bases can hydrolyze in water to affect the pH, and how the ammonium ion can affect the pH in a solution. All right, we'll practice this in class.